Okay, today we're going to talk about rational functions and their graphs. So it's sort of hard to do this stuff without being in class, but I do think you should have some sort of knowledge. We'll do a lot, we take it a lot more in depth in pre-calculus anyway, but you should understand that you can have these fractions. So we know that we have a rational expression is, I could say, P of X over Q of X. And you know Q can't be 0 because you can't divide by 0. Well, we make it a function by saying f of x equals that. Okay, so if we have f of x equals P of x over Q of x, Q of x cannot be equal to 0, we can talk about the graphs. Now, the notes that I've attached to you, they say the simplest is ax plus b over cx plus d. And that is the simplest because they're linear. But if I was doing this in class, and again, you'll see it next year, the simplest rational function is 1 over x. And what 1 over x graphs as is has a horizontal asymptote, a vertical asymptote, and you have these two branches. So it's not continuous, it's a broken graph. But the minute we bring in any polynomials, it becomes a lot more in depth, and you can get these pictures that are really strange. What I want to make sure we talk about is the domain. So when we say what is the domain is anything that works. So if we think we have a fraction, what won't work is things that would give you 0 in the denominator. So if I just looked at a couple and explained the ones that were on the notes, you have x over x plus 3. Well, you got to think, okay, what would not work? Well, if this was -3, that would give me 0. So I could say all real numbers except x equals -3. The easiest way is do a double stemmed r like that. Now, how do you find that if you can't find it? Think of setting the denominator equal to 0. We did this with when we added, subtracted, multiplied, and divided. We had domain restrictions. Well, that's really, x cannot be -3. If I gave you these are on the notes. If I gave you 5 over x minus 6, well, what could x not be? 6. Because if that was 6, I'd get 0. All real numbers except x equals 6. Now, if you have a quadratic on the bottom, something like that, or I think that was a 4, both of those could give you 0. So you would have to say all real numbers except x equals 1 and -4. Now, if I gave you one that wasn't factored, and so this was x squared minus 7x plus 12, this was x squared plus 9x plus 20, you have to think, okay, what can give me 0? Well, this is easy to say, oh, 6. Well, if I think of setting the denominator equal to 0, how do I solve that quadratic? I factor. So x plus 4, x plus 5, So I get -4 and -5. So if I say, what is the domain? What can I put in? I can put in anything except -4 and -5. So that's the domain idea. Then we talk about, in the notes, they talk about discontinuities, horizontal asymptotes, vertical asymptotes. So, if you think of that graph I looked, you're going to have these asymptotes that these graphs get closer and closer to and don't touch. Your vertical asymptote is always at your domain issue. Now, domain issue could be a hole, which is a discontinuity, but as long as nothing crosses off. So if I gave you something like x over x minus 3, that cannot be simplified at all. If I say, where is your vertical asymptote? Your vertical asymptote is at the 0 of the denominator. X is 3. Think about it. Domain, x can be anything except for 3. So what that means is my graph is never going to touch 3. So I'm going to have this vertical asymptote at 3. Now with horizontal asymptote, which again, this isn't that major, but I do just want to make sure we touch upon it. Horizontal asymptote is dependent upon the degree, which is the highest power, of the top and the bottom. So you look at the degree. If the degree of the top, so I'm talking about like P of x over Q of x. If this is less than the bottom, your horizontal asymptote is automatically y equals 0. So these examples, 5 over x minus 7, that has a 0 degree, a first degree. X to the first, horizontal asymptote, y equals 0. Second one, 3x minus 1 over 4x squared minus 9. The degree of the top is 1. The degree of the bottom is 2. If the top is less than the bottom, horizontal y equals 0. Automatically, no thinking. Now, if the degree of the top is equal to the degree of the bottom, so an example would be something like x plus 2 over x minus 2. Those are both to the first degree. Your horizontal asymptote, y equals, is the leading coefficient divided by the leading coefficient. So that would be y equals 1. If I gave you 2x squared minus 5 over x squared minus 7x plus 12. The degree of the top is 2. The degree of the bottom is 2. They're equal. It's the leading coefficient divided by the leading coefficient. Y equals 2. Now, if the degree of the top is bigger than the bottom, so like if I change that to a 3, you don't have a horizontal asymptote. You have something called a slant asymptote, or it could be a parabolic asymptote. That is pre-calc. We're just talking about vertical and horizontal. Now, discontinuity or a hole in your graph occurs when there's a common factor in the top and the bottom. So an example would be something like x squared minus 9 over x plus 3. Or x minus 3 is, I think, what you guys see. So if you think domain, x cannot equal 3. So it'd be all real numbers except x equals 3. But if I said, well, is there a vertical asymptote? Usually you would think it would be at x equals 3. But if you simplify the top and simplify the bottom, that crosses off. So you really, if you plug this into a graphing calculator, you're going to see something that looks like that. But if you went to the table, you would see error at -3, which means at -3, there's a hole in your graph, but you don't see that when you graph it. Again, that is higher kind of level stuff, but it gives you an idea of the graphs. So all I'm going to really ask that I think is important, me giving you a function such as 3x minus 1, 4x squared minus 9. I say to you, give me the domain, vertical asymptote, point of discontinuity, horizontal asymptote. And not really graph it, just tell me what these things are. So domain, everything except where the denominator equals 0. If I set that equal to 0, I could factor it, 2x minus 3, 2x plus 3. So it's going to be all real numbers except x equals 3 over 2, negative 3 over 2, or plus or minus 3 halves. If I say, what's the vertical asymptote? You either have a vertical asymptote, or a point of discontinuity, or you could have both. But if you think, nothing crosses off. So if you have 2 domain restrictions, that means you have 2 vertical asymptotes. So really, if you were graphing this, you'd have a dash line at 1.5, a dash line at negative 1.5. There is no point of discontinuity. Horizontal asymptote, look at the degree. The degree of the top is 1, the bottom is 2. If the degree of the top is less than the bottom, y equals 0. Done. So then just one more, even though I know it's sloppy. And if you had a graphing calculator or Desmos, you could put that in and see what it looks like. 2x squared plus 2 over 9x squared minus, let's say 4. So, domain. Find your domain by setting the denominator equal to 0. You can either factor that or add 4 divided by 9 square root. All real numbers except x equals plus or minus 2/3, because it's going to be 3x minus 2, 3x plus 2, solve for 0. You don't have a common factor, so your vertical asymptotes are the same as those. X equals plus or minus 2/3. No point of discontinuity because we have nothing to cross off. Horizontal asymptote. The degrees are equal. So your horizontal asymptote is going to be y equals 2/9. The biggest thing really with the ACT, with the graphing of these, is you know how to put it in your calculator. So they really don't ask you for the graph. They ask you more for the domain, or what are the restrictions? So those are your restrictions. The numbers that you would put in for x, and they would give you 0. So that's a little explanation. We'll talk Friday morning about any questions with this.